In this video, we'll be talking about the triangular distribution, and it's kind of an extension of the continuous uniform distribution, except that you see that we have 3 parameters instead of 2. So back then we had the parameters a and b to give the endpoints of the interval we were dealing with. Now we have these a and b, which are still the endpoints of the interval we're dealing with, and we have a new value c, and c must lie between a and b. Okay, so now let's draw a picture. Usually we draw pictures at the end, but let's draw it right now because it's really going to help us see what a triangular distribution is. So I'm going to go ahead and draw a graph. This is going to be actually the PDF. So we're going to have f big X little x, and we're going to have little x down here. Okay, so the PDF of a triangular distribution looks like this. We're going to pick the endpoints. Again, it's going to be a and b. Okay. And we're going to pick a value c where we think that the PDF is highest. So the density is it's highest at this point c, okay? So we could just get an intuition of this by thinking of a little bit of a similar case to what we were thinking of before. So before we were thinking of a car traveling from A to B, stopping at a random point, and the point it stopped at was equally probable for any point from A to B, okay? And it's impossible for it to stop before A or after B. Now we have the same kind of thing. Let's say it's a runner instead of a car. So he's running from point A to B, and let's say he stops because he gets tired at some point between A and B. Now, if that's all there were, then we would say that it's equally likely for him to stop at any point from A to B. But let's say at point C, he finds there's $10 on the ground. So he's more likely to stop at C because he gets tired and there's money there. So maybe it's more likely to stop at C. So if we send thousands of runners from A to B, let's say many of them would stop at C. Okay, so most of them would stop at C. So that's kind of gives us an idea that maybe C is an important point, has the highest density, but it doesn't tell us much other information. So we capture that in a triangular distribution by putting this peak at C and just saying that starting at 0 at A, going up to this peak, and then going back down to B. And this is why it's called triangular distribution, because we get this triangle here. Okay, so this is our PDF, and let's say on all the points of the line, so over here and over here, we see that it's 0. Okay, so we're only concerned on the interval from A to B. Now the next thing we got to do is find the PDF of this. It's not so hard because the graph is sitting right in front of us. All we need to do is just use our slope intercept type of algebra formulas to find the slopes of the equations of these lines. Okay, so there's just 2 lines to worry about. Let's do this one first. Now, what are 2 points on the line? We have A0 is 1 point on the line, and another point on the line is C and what? We don't know what this height is. Now that seems problematic at first, but we see that it's easily findable because we see that since this is a PDF, this whole area down here must integrate to 1. So we don't even need to use any integrals because it's a triangle. We'll just use the area formula. So base times height over 2. Base is b minus a. Height is the thing we want to find, so we'll call it h for now. Divided by 2 must equal 1. We see the height is easily given by 2 over b minus a. So we're going to put 2 over b minus a here. Okay, so we're still trying to find the equation of this positively sloping line. So we find the slope of it is rise over run. So the rise is 2 over b minus a, the run is c over c minus a. So it's 2 over b minus a, c minus a. That's the slope. I'll call it m1 for the positively sloping line. Okay, so we're just going to say it's y. We're going to use the point slope formula. So y minus y is this, which is 0, equals the slope. So it's going to be 2 over b minus a, c minus a, x minus the other point. So it's going to be a. And this is our PDF for the first part, easily found. Now let's do the other one. So doing the other one, we see that, again, we want 2 points. So we're going to use this point is actually common to them because we see it's connecting them. So we have c, and again 2 over b minus a, and we have the point b, 0. So again, we want to do the slope. What's the slope? It's going to be rise, which is minus 2 over b minus a over the run, which is b minus c. Okay, that's m2 for the negatively sloping line. Okay, cool. Now let's do the same thing. So we have y minus 0, so it's going to be right there, equals minus 2, which is, this is the slope right here, x minus b. Okay, so this is our 2 PDFs right here. So let's write that in a more concrete form so we have a nice formula. So we have that the PDF, again written in this form we're usually writing it in, is 3 components. The first is the positively sloping line, so it's 2x minus a over b minus a, c minus a. The second is the negatively sloping one. I'm going to leave this negative here instead of absorbing it here so we can clearly see it's the negative one. Over b minus a b minus c, and the last is 0 otherwise, as we usually have. Now, when are these two holding? So this one is holding when we have the positive portion, or a to c. So a less than or equal to x less than c. Now this portion is holding on the negative, so we have c to b. So it's c less than x less than or equal to b. Now almost done. We just have to pick which one we want to incorporate c into. We see it doesn't really matter, because if we plug in c here, we want to get h, or 2 over b minus a. What if we plug in c here? We get c minus a on top, c minus a on bottom. These cancel. We get 2 over b minus a. That's correct. Now if we put c into here, we get c minus b up here, we get b minus c up here. They cancel and generate a negative sign, which we apply to this, and we get 2 over b minus a. Same thing. Doesn't matter where we put it. Let's put it here. We can put it there if you want. Okay. So we have this PDF right here. This is the PDF of a triangular distribution. Now we could go through and do how we usually did. We can find the mean expected value and MGF, but it turns out to be a lot of algebra, and that's because we have to do it for two separate segments. But the process is straightforward. For example, how do you find the expected value? All you have to do, you have to integrate over the whole real line. And we found that really you just have to integrate from a to b because it's 0 everywhere else. And now integrate from a to b is a little bit trickier because you have to do two subsegments from a to c and then c to b because it has different equations for the PDF there. But if you work through all that nasty kind of algebra, you'll find the answers. I've written for convenience on the back the 3 answers, and instead of deriving them, what we'll do is just analyze them and see what changing some things can do. So the expected value first is given by a plus b plus c over 3, which is kind of nice because the uniform one was given by a plus b over 2, so this is pretty easy to remember. You just have to add the extra parameter and divide by the number of parameters we have total. So what I started drawing a little picture. I was saying, what if you changed c? What if you increased it by a little bit, and just by a little bit, because you don't want to put it past a b, and this won't be triangular anymore. Okay, so if you increase it by a little bit, so the original c was here, I increased it to c prime, and in dotted lines, I've drawn the new triangular one. So how about instead of dotted lines, I draw it in gray, so we can kind of see it more concretely. So, looks just like that. So the gray one is the new one, the purple one's the old one, okay? So we see that by increasing c, the mean has definitely shifted to the right because I'm putting more of the distribution, I'm pulling it this way. I'm kind of pulling a lot of it over here. So likewise, if I had decreased c, I would be pushing the distribution that way, thereby decreasing the mean. I know that's not precise mathematics, but it's very intuitive to see what's going on here. So now let's see the variance. The variance looks kind of nasty. It has a very symmetric form though, so it's the parameters squared, a squared plus b squared plus c squared, minus the pairings of the parameters. Okay, so we have minus ab minus ac minus bc. So it's all the 3 combinations you can make with them, divided by 18. Now this 18 is probably kind of hard to remember, but you try to commit it to memory just how you committed this the 12 to memory in the uniform b minus a squared over 12 for the variance. But we can see again how would the variance change if you change different things. Okay, so what if we did a little experiment? What if we decided to double a? So let's do it underneath, and I'll explain the MGF in a moment, but let's do the variance. If we doubled a, then we would get up here 4a squared, and all these b terms, c terms don't change. Now up here we get minus 2ab, minus 2ac, minus bc, because the bc doesn't have anything to do with a, all over 18. Now all I really want to see is how is that changed from the original variance. So the extra stuff we add is 3a squared, and we add a minus ab and a minus ac all over 18. So now the real question to ask is this positive or negative? That is, has the variance gone up or gone down? It's still pretty unclear. Let's do something. Let's factor out an a over 18. So we have a over 18, 3a minus b minus c. Okay, now we want to ask the question, is this positive or negative? Let's say, just to make a simplifying assumption, that we're only considering values of a, b, and c that are positive. That need not be the case. You can consider negative ones. We'll just do positive for the sake of this. So that means that a over 18 is positive. So if this whole thing's to be positive, then this must be positive also. So under what condition is 3a minus b minus c greater than 0? We see that using algebra, the only way is for a to be bigger than b plus c over 3. So we see that the variance increases only if a is bigger than b plus c over 3. Now this is interesting because if this was b plus c over 2, then this number, this b plus c over 2 in that case, would have to lie between b and c. but that's not the case. There's many numbers you can pick such that b plus c over 3 is less than b, for example. So in picture-wise, what does that look like? So we have a, b, and c, if a is bigger than b plus c over 3. So if we have b here and we have c right here, so now let's say we have a little picture here. We have c over here, so I'll put c here and we have b here. Then where would a have to be for the variance to increase with a doubling of a? So we see that a has to be greater than b plus c over 3. Let's say b plus c over 3 lies right here. So we'll put b plus c over 3. So in other words, if a exceeds that, so if a is within this range here, then a doubling of a will cause a positive increase, a positive change in the variance when we do that doubling of a. Otherwise, it'll cause a negative change. So it really depends. It's not clear cut. Just a little bit of an exploration, okay? And the MGF, again, it's pretty nasty, but the way you calculated it is pretty clear. You just do expected value of e to the sx. Actually, here I've used t instead of s. So normally what we call s is being played by the role of t. No change, just a different variable. So it's pretty complicated, and actually a little caveat I should add, if we put in t equals 0 here, we see that we're going to get a little bit of issue because the denominator becomes 0. So maybe I should put, this is for t not equal to 0, and what will have to be if t equals 0? That's a quick check, and maybe it's complicated. What if we don't know? But if we look at the formula for MGF, expected value of e to the sx, actually, let's put t. If we put t equals 0, that's expected value of 1, which has to be 1, right? That's a sanity check. So we have to put 1 if t equals 0. This is a pretty complicated formula, but I mean, it has a nice symmetry to it as well. It's just 2 times b minus c, here's a b minus a, c minus a, e to the at, e to the ct, e to the bt. Just be careful of this minus plus sign difference right here. Okay, so since the triangular distribution is not as popular as the uniform one, we don't need to delve into it as much, but it's a nice exploration to have, and it's a little bit of a better, much better approximation when you know what's the highest density thing, because then you can kind of create this better model. Because if you didn't, then we would just have all this area concentrated in a uniform distribution from A to B with no idea of which is the most common value. So this is a good distribution to know.